I want to do an example where we do a substitution in a triple integral and then evaluate. And what I've chosen to think about is the volume of this ellipsoid. And so I can draw an ellipsoid badly, but we'll just pretend. All right, so we're going to pretend that's actually an ellipsoid with an origin right there in the middle and the z-axis coming out here, and that being the value c, and making minus c down here. And there's my x-axis and the distance a, minus a, and finally a y-axis. So there's an ellipsoid in a right-handed coordinate system b, and back here minus b. And so I'm supposed to find the volume of that. And so I could imagine a triple integral in rectangular coordinates just the way this is situated to do that. Now, I'm going to go on and think about just finding the volume in the first octant and multiplying it by 8. And that way, all my lower bounds would just be 0. Since I'm finding a volume, I can just think about dz, dy, dx. All right, well, if I imagine an array that goes through the first octant, I would hit the floor, right, just that bottom part there, in the xy plane, and then I'd hit the ellipsoid, just remembering that I'm only thinking about this part here that lies in the first octant, that 1/8 of the volume. And so I'd need to solve this for z, and z would be equal to the square root of c squared minus c squared over b squared x squared, over a squared x squared, and then minus c squared over b squared y squared. Not a very nice expression there. The first round of integration wouldn't be particularly hard, but that would probably be fairly challenging past that. And now I need to imagine the projection into the xy plane. And I would get an ellipse, or that little quarter of an ellipse in the xy plane, going from 0 to a and from 0 to b on the y-axis. And I would start at 0 and then go through the equation of the ellipse I would get in the xy plane. Well, that would be x squared over a squared plus y squared over b squared equals 1, which I would then have to solve for y. And so this top bound, I didn't give myself a lot of room to write it, so I have to kind of write it in here a little oddly, would be this. And then finally in the x direction from 0 to a. And if you're comfortable integrating that, go on and do it. But I was thinking about trying to use a clever substitution, trying to make this problem just a little bit easier. And so what I'm going to do is I'm going to choose the substitution x equals au, y equals b times v, and z equals c times w. Because what this does is when I substitute these in, I get u squared plus v squared plus z squared equals 1. I get a unit sphere in a UVW space. So I just get a sphere of radius 1. A much easier region to think about. Instead of an ellipsoid, now I'm dealing with a sphere. So this triple integral through this substitution, instead of integrating over the ellipsoid, I'm integrating over a unit sphere. 8 out front would have to stay out front. I'll have to rethink my bounds, and then this dz, dy, dw would become a dw, dv, du, in whatever order you actually want to do those in, but times the Jacobian in absolute value, right? So I might have a different scaling factor. So even before I find any of the bounds, let's calculate the Jacobian based upon this substitution. So the Jacobian is equal to, all right, so I take the partial of x with respect to u, v, and then w. Well, that would be a and then 0 and 0. Take the partial of y with respect to u, v, and then w. Well, that would be 0, b, and 0. This is a great Jacobian to have to evaluate, because I can think about expanding over that top row, and I would get A times, and then the determinant of this little guy, B times C, and I just get ABC. In fact, it's a fact that if you take the determinant of what we call a diagonal matrix, where the only values are on that main diagonal, you get the constant, you get the product of those things. So ABC is my Jacobian, and so this triple integral for volume I'm dealing with is volume equals 8. And I should write down ABC there, but those are constants, so I can imagine pulling them out front. So 8 times ABC times the triple integral over this, which I'm just going to call B for a moment, right? Literally a unit ball. And now that's a dw, dv, du. Well, this triple integral is literally just asking me for the volume of that ball, right? That's what this is. It's the triple integral over the differential operator dv. And so after my substitution, I don't even have to really integrate. I know the volume formula for a sphere, 4/3 pi r cubed. The radius is 1, so I get I'd get 4/3 pi, but now I remember I was only going over the first octant, so I'd still be going over the first octant, so it's 1/8 of that. The 8's cancel out, and I get 4/3 pi times A, B, C. And if I think about it, this formula feels good, because if A, B, and C are all the same thing, instead of an ellipsoid, I have a sphere, and that would be 4/3 pi r cubed. All right, so we found a formula for the volume of an ellipsoid by using a substitution and calculating a Jacobian, and then realizing that this would just be the volume of 1/8 of that sphere, right? Because I was reduced to the first octant.